previous class revision. So please pay attention. So in the previous 2 classes, we are learning the 4th chapter of this physics volume 1, where we have learned about moving charges and magnetism. I started teaching this chapter with the introduction of Biot-Savart law to you, which states or which is helping you to find the magnetic field due to a current element. Current element is a small portion of the wire which carries the same current as carried by the whole wire, and we found that small magnetic field dV produced by the current element dl is given by the formula mu naught by 4 pi I dl sin theta by r square. This is the scalar form of Biot-Savart law. If they ask you what is the vector form of Biot-Savart law, then that is dB is equal to mu naught by 4 pi I dl vector cross r vector by r cube, because dl cross r will give you dl r sin theta, and r will cancel with one r down, and it will once again become the same thing. So remember, Biot-Savart law is mu naught by 4 pi I dl sin theta by r square. Then we learned what is the magnetic field due to a straight current carrying conductor. I gave you the mother formula, not required for you, but I told you it is mu naught I by 4 pi r into sin theta 1 plus sin theta 2, where theta 1 and theta 2 are the angles subtended by the point where you are finding the magnetic field with the topmost point and the bottommost point of the wire. It is not required for the school examination, even though I told you. And if you put the values as for infinitely long wire, you will get the magnetic field due to a straight current carrying conductor as mu naught I by 2 pi r. So remember that for a straight current carrying conductor, r distance away from it, the magnetic field is mu naught I by 2 pi r. Then we derived by using the Biot-Savart law what is magnetic field due to a circular current carrying conductor at its center, and we got the value as mu naught I by 2 r. After that, I told you what is magnetic field due to circular current carrying conductor at an axial point. We derived it, a long derivation, important derivation. It took almost half an hour for me to teach you that, and the final expression was B is equal to mu naught I a square by 2 into a square plus r square power 3 by 2, where a is the radius of the circle, r is the axial distance of the point where you are finding the magnetic field from the center of the circle. In the same thing, if you keep that r is equal to 0, you will get the value of B as mu naught I by 2 pi a, because a is the radius, not 2 pi a, 2a. So always remember, for a straight wire, r distance away from it, magnetic field is mu naught I by 2 pi r, and for a circular wire at its center, magnetic field is mu naught I by 2 r, right? And for axial distance, mu naught I a square by r square plus a square, 2 into r square plus a square power 3 by 2. I also taught you different kinds of question that comes in the board exam from this topic. This topic is very important, and I told in the class also, and even in the worksheet class, practice class, ma'am would have solved some questions based upon that, because in the previous year books you have many questions from that topic. I told ma'am to focus on those questions, and I hope you have understood how the questions are coming in that chapter, that topic. Then in the previous class, I started talking about force on a moving charge kept in a magnetic field. I told you a static charge experiences no force in magnetic field. So in magnetic field, the static charge will experience no force, nothing will happen. If you have a proton kept here and magnetic field applied, nothing will happen to proton, it will remain as it is. But the moment you keep a moving charge in magnetic field, it will experience a force. What kind of force it will experience? Lorentz force. What it will make it to do? It will make it to go in a circular path. If it is uniform magnetic field, and if the charge enters the magnetic field perpendicular to it, then what starts to happen? The charge starts moving in a circular path. Why it happens? I told you, Fleming's left hand rule. Whenever it is trying to go in one direction, the force will push it, and finally it will take a circular path, and the radius of this circular path r is equal to mv by qb, where m is the mass of the particle, v is the velocity of the particle, q is charge of the particle, and b is the magnetic field of the particle. If the question is coming like, in a uniform magnetic field you have a proton and a helium which will have a bigger radius, then r is equal to mv by qb. Q for helium is more compared to proton. Since q is more, it will have a lesser radius. Since q for proton is less, it will have a bigger radius. If velocity, but m also changes, sorry, m is also different, right? So, to find the ratio properly, because m for helium will be 4 times of the protons, isn't it? So, above 4 will come, and below how much will come? Below mass is there. So, mass of proton is double, and like that charge is double, I think, and charge is double and mass is 4 times. So actually it will increase, sorry. Helium will have a bigger radius, double the radius of hydrogen. Are you getting what I told now? R is equal to mv by qb. M for hydrogen is 1e, mass of only one proton. But helium will have 4 times the mass of proton, isn't it? And in the case of charge, for proton it is having only e charge, that will have 2e charge. So charge becomes 2 times, but mass becomes 4 times. So if you cancel, it will become only 2 times. So 2 times in numerator. It means that radius for a helium will be double compared to hydrogen if they both are entering the uniform magnetic field perpendicular to it. Then I taught to you what happens if a charge enters the magnetic field making a random angle theta, and I told you the charge starts getting a helical path and the radius becomes mv sin theta by qb. Time period and frequency remains same, and there is a pitch is equal to 2 pi mv cos theta by qb. These things we learned in the previous class. And then actually by using Biot-Savart law we also found this thing here, Ampere circuital law also we learned. In the previous classes we learned about Ampere circuital law, which says that the closed integral of B dot dl is equal to mu naught times the current enclosed by the Amperean loop. B dot dl is equal to mu naught into I. And I taught to you the magnetic field due to a solenoid also, which is B is equal to mu naught Ni, where N is the number of turns per unit length. Don't forget this. I think this is what we learned in this chapter up to now. And today we are going to proceed from there, and our aim is to finish this chapter by today. Today's class is going to be the last class for this chapter, if everything goes as per the plan. So give the heading as, today's class first heading is force on current carrying conductor, kept in a magnetic field, So what we are going to do now, we are going to find what is the force on a current carrying conductor kept in a magnetic field. In the previous class we found what is the force on a moving charge kept in a magnetic field, and what we got in the previous class, we got the force on a moving charge as q v b sin theta. You remember this? If I write in vector form, then f vector will become equal to q into v vector cross b vector. You remember this or not? I hope you remember this. Moving charge force, the value is this much, q v b sin theta. Coming back. So imagine, please everybody pay attention. Imagine you are having a current carrying conductor, okay, and for simplicity I am assuming the current in the conductor is in the direction which is towards the right of it. And what I am going to do, I am going to place it in a place where the magnetic field is acting in the upward direction. If I draw the diagram, it is something like this. I am drawing the diagram of magnetic field. So the diagram of the direction of magnetic field is like this. You are able to feel what I am doing? So magnetic field is from down to up like this, and I am keeping the conductor like this. It is a current carrying conductor, okay. If it is a current carrying conductor and the current is moving in the right hand side direction, if I take the moment of positive charge, then the moment of positive charge will happen in the same direction. Do you agree with me or not? Do you agree with me? And negative will happen in the opposite direction. Okay. Now the magnetic field is acting in this direction, and charge, if I am taking one positive charge, it is moving in the right hand side direction. So here, since, why this happens very frequently, Revan sir, one thing, down in the main board there is a changer we have put now. You have seen the main board, no? There are fuses there. Yes. In that recently we have put a changer. So I think it is in 2 now. Change in 1 and 3 and check power comes or not. Power is there in some phase. Not came, not came. No, norm also not came. Not coming in any phase? Not coming in any phase?
Not actually, I changed to one and three. Sir. Theory was two.
Huh.
Changed to one and three.
Not coming in any phase. Aha. But power is out in other places also.
Yes, sir. Yes, sir.
Huh?
Yeah.
But power has resumed back, so all of you please on your video once again. If you are hearing me, all of you please on your video once again. I hope you are able to view me, right? So Shaktivel, Saravanan, if you are hearing me, make sure your video is on, or we have to put you in the waiting room. Make it fast, guys. Yeah. So what I was telling to you, I was talking about a conductor which is placed in uniform magnetic field. So I said the magnetic field is acting in the upward direction and the current is acting in the right hand side. Okay. So if you use your left hand where my magnetic field is given by my first finger and current is given by my middle finger, then the force will be acting in this direction. Do you agree with me? Which direction? Towards you, towards us. So if I draw a three-dimensional plane, can I draw here? This is the direction of current, this is the direction of magnetic field, this will be the direction of force. Do you agree with me? Obviously yes. But this force is acting on a particular charge, on a single charge. If I assume n to be number of charged particle per unit volume, the same thing which you do in the earlier cases, per unit volume, then what is the meaning of n? N becomes n by v. Do you agree with me? So if I ask you what is the total number of charges n, you will say it is n times v. So you will say it is n times, what is v? Area into length. Don't you agree with me? Length of rod is taken to be L and its area of cross section is assumed to be A. So can I say its volume will be A into L? So the number of charged particles is n into A into L. Total force on the conductor will be how much? First of all, first tell me what is the force on each charge. Force on each charge will be how much? QEB sin theta. So it will become equal to Q, which is E, into V into B, isn't it? And sin theta, let it be sin theta itself. So can I write now total force will become equal to F is equal to n times of this E, V, B sin theta. Do you agree? And what is n? N is NaL. So F will become equal to NaL E V B sin theta. Don't you agree? What is NEAV? V is what? Drift velocity. V is the velocity with which the electrons are moving, drift velocity. What is NEAVD? Third chapter, I. So can I say that? Shy. Very difficult. You can pause it. Am I audible to you guys, those who are in the online? It was second power cut. But good thing is, once again power came back. Some of you are thinking that if power cut is happening, that why they don't have a backup facility for having the class. So studio is running on almost 5,000 watts of power, and 5,000 watts of power, it's not easy to give by any battery or inverter. We have inverter already here, but inverter is not capable of giving, you may say generator, right? Yes, good. What power should not go again? What, man?
Sir, for the derivation, first we count the force on one charge particle and then percentage for the whole volume of the.
Thank you, man. Thank you. So I'll, yeah.
Doubt, sir.
Oh, you're asking out. I thought you were telling me. Yeah, tell me, man. Yes.
That only I'm asking.
What, man?
That,
Why are we doing that? You're asking.
no, sir.
Then?
That's only correct.
Yes, man. That's correct only. Yes. What we did, as told by Mr. Sharan Ram, when you are keeping a current carrying conductor in a uniform magnetic field, and this magnetic field was acting in the y direction, current was acting in the x direction. Oh, you people came now only, no? For you, good only. I taught something, I am repeating it once again. So I took a conductor which is carrying a current towards the right hand side. So current is acting in this direction. Which direction? X direction. And magnetic field is acting in y direction. By the left hand thumb rule, current being here, magnetic field being here, the force on the charge will act towards you, that is in this direction. This will become z direction, isn't it? Positive z direction, this side. This will be direction of force. But this force will be acting on a particular charge, and I took small n as total number of charge per unit volume, from where I wrote number of charged particles is n into V, and volume will become equal to area of cross section into length of the wire. So I can write number of charged particle is what is n into A into L. This was total number of charged particles. So if I want to find charge on one particle, I said charge on one particle will become equal to E into V into B into sine theta. So the force on all the particles will become N into E into V into B into sine theta. And then what is N? N is small n into A into L into V into B into sine theta. And you know very well, N E A V, which actually it is drift velocity only. So N E A V D will be how much? I. So force will become I into L into B into sine theta. Always remember that if a current carrying conductor is kept in a magnetic field, the force acting on that current carrying conductor is ILB sine theta, where I is the current carried by the conductor, L is the length of the conductor, B is the magnetic field acting on the conductor, and theta is the angle made between direction of current and the magnetic field. Remember that. This is the formula ILB sine theta, or if you want to write in vector form, F vector will become equal to I into L vector cross B vector. Length is not a vector quantity, but here we are taking vector quantity, but generally it is not considered to be vector quantity as a length. So remember this, I into L cross B. Clear to you? If yes, copy it fast. If it is clear to everybody, please copy fast. I'll mark the attendance. Yes, what you are asking, Yogit? Hmm. Which one is?
Immaterial.
Hmm.
They have given option like resistivity, radius, length, and temperature.
Resistivity, radius, length and temperature. Which of the following is immaterial for a resistivity? Obviously, resistivity.
Low resistivity should be there.
Tell me in the options what you are saying.
Resistivity, length, radius, and temperature.
See, if length is changing, resistance will change. If radius is changing, resistance will change. Remember one thing: fuse wire should not have it should have low resistance, isn't it? Fuse wire should have high resistance and low resistance and high melting point. Is it so? Fuse wire should have like that. Why it will have high melting point? Yeah, low melting point and high resistance. So high resistance, why? Because it has to sense the current coming inside. And why low melting point? It should melt if extra current is coming inside, isn't it? So if you talk about all these things, R, that is radius, length affects the resistance, even the temperature affects the resistance. So resistivity is only which is immaterial for fuse wire in all these four things. Got my point? Because all the properties is going to affect the resistance, and fuse wire should have a high resistance and low melting point. Are you getting a point? Okay. So all of you have copied this? Copied this or not? So what we understand? We understand that if you have a conductor, please understand this, if you have a conductor, if it is carrying some current like this, that is, there is a conductor carrying current in the right hand side direction, and if suppose magnetic field is acting in the upward direction, then the force on this conductor will act in this direction. So automatically it starts moving towards you. And once again, direction of force is found by which rule? Fleming's left hand rule, where first finger is giving direction of magnetic field, middle finger is giving direction of current, and thumb is giving direction of force. Is it clear to you? I hope you are getting my point. If you stretch your three fingers in such a way that your first finger is giving direction of what? Magnetic field, middle finger is giving direction of current, then thumb will give direction of force. So in the last two topics, the previous class and today's class, we have understood that if you have a charge kept in, moving charge kept in magnetic field, it will experience a force of QEB sin theta, and if you have a current carrying conductor kept in magnetic field, it will have a force of ILB sin theta. Okay, proceeding further. Now let us understand what happens if you have two wires. Please pay attention, something important. If you have two wires and these both wires are carrying current in same direction. Why? That's what we are going to learn now. They will attract you, right? Why? Let us learn about that. So give the heading as force on two parallel current carrying conductors. Two parallel current carrying conductors. Please pay attention. After write the heading, drop your pens for 2 minutes. Let me explain to you and then you can copy it. Shall I? All of you? I hope you are ready with listening. Something very important, and question comes from here in the board examination. Definitely comes from here. You see, last 10 years, 7 to 8 years questions come from here. So please pay attention. What I am doing, I am taking two wires which are carrying current in same direction. Let them be wire A and wire B. Okay. Now we are going to use lot of rules here which we have learned in the previous classes. When I taught to you when I taught to you magnetic field due to straight current carrying conductor, I said this topic is removed from syllabus of NCERT. It's not there in syllabus, but they are going to use in future. Now they are going to use it. So please pay attention. You must understand that if you have a current carrying conductor, then because of a conductor carrying current, there will be magnetic field around it. So by the current in the wire A, let the current be I1 and here let the current be I2. The conductor A is carrying current I1 in this direction. What will be the direction of magnetic field at on the wire B? By using, why left hand you are using, man? We are finding magnetic field direction. So you should use right hand thumb rule only, no? So current in this direction, magnetic field trying to go inside into the plane. So can I say that here the magnetic field will be into the plane? Do you agree with me or not? Do you agree with me? Same way, if you have magnetic field into the plane and current is going in the upward direction, now pay attention. We will use left hand rule and magnetic field into the plane, current in the upward direction. Which side the force is acting? Towards left. So there is a force going to act on the wire which will make it to move towards left. Now same way, by using right hand rule, the current I2 in wire B is going to produce magnetic field in the out of the plane on wire A. Do you agree with me or not? If I have a current carrying conductor like this, if I ask you this side, how is the nature of magnetic field? You will say out of the plane. This side into the plane. That's all I am using now. So because B wire is carrying current in the upward direction, because of current I2 in wire B, magnetic field on A will be acting out of the plane. I hope you are agreeing with me. Now by using left hand rule, magnetic field is acting in the upward direction, outward direction, and current is going in the upward direction. My thumb is pointing towards my right. The force is acting towards this. So if two wires are carrying current in same direction, they will start attracting each other automatically. Why are they attracting each other? Because of the force acting on them. And why is the force acting? You are clear in that? Because of this wire carrying current, we have a magnetic field towards right in the into the plane direction. Magnetic field is known, current is known, force can be found by using left hand rule. Because of current in wire B, there is a magnetic field on wire A, magnetic field is known, current is known, force we can find. And we will be finding the force, we will come to know that force will act in such a way that both wires are attracting each other. With how much force? Let us try to find that also. Because how we have to find step by step. Please understand this derivation, then you can copy it. No problem in writing anytime. Anyhow, this video is going to be there. So please pay the attention in the derivation part. So first what I am going to do, I am going to find magnetic field on wire B. Magnetic field on wire B due to current I1 in wire what? A. Do you agree with me? How much will be that? Mu naught I1 by 2 pi. Let distance between them be d. So I am taking it as 2 pi d. Do you agree with me? Any problem in this? What formula are you using? Mu naught I by 2 pi r. Okay. Now, what will be the force on wire B? That will become equal to ILB sin theta. Just now we learned ILB sin theta. So it will become I is how much current? I2 in the wire B. L into B. B will be how much? How much? Let us try to put it the value. I2 into L. What is B value? Mu naught I1 by 2 pi into d. Do you agree with me? So how much you are going to get? Mu naught I1 I2 L by 2 pi d. This is the force on wire B. You agree with me? The force on wire B is mu naught I1 I2 L by 2 pi d. Same way, if you try to determine what is the force on wire A, so how I'll do? I'll do magnetic field on wire A due to I2 in wire B. How much will be that? Mu naught I2 by 2 pi d. I hope you agree with me. Same thing, what is the force on wire B, wire A actually? Force will become ILB sin theta. So I1 into L. What is B? Mu naught I1 by 2 pi d. You will be surprised to know that it is same mu naught I1 I2 L by 2 pi d. It means both the wires are attracting each other with the same force. And how much is the force? Mu naught I1 I2 L by 2 pi d. So now you understood that if there are two wires carrying current in the same direction, they will be attracting each other with what force? Mu naught I1 I2 L by 2 pi d. If they ask you what is force per unit length, it is given by the letter small f, force per unit length, that will become equal to mu naught I1 I2 by 2 pi d. Is it clear to you? Is it clear to you? I will tell you now how the questions are coming in the board exam from here. First you copy it fast. Make it fast, make it fast, make it fast. What sign? What positive and negative? So they'll cancel each other, you are saying. Yes, one second. Huh? Where? Here? Okay. Something you say, Anshul? Anshul, can you say something? Revan sir, can you put the output of mic? I think it is not in TV. Yes, now I think. Anshul, speak something.
Sir,
Yes.
I didn't ask him.
No, you not asked anything, but I asked something to you, man. How, like, exam started in school now, or is it going to start next week?
Next week, sir. Next week.
What is the portion for the exam for physics?
First three chapters.
1, 2, 3 only, no?
Yes, sir.
But in school they are teaching electromagnetic waves, if I am right. No,
Yes, sir. Chapter 7.
7 is not electromagnetic waves. Not, don't say yes, sir then.
Sorry, sorry.
Cha-
Chapter 7.
chapter 7 is alternating current, isn't it?
Yes, sir. All training times.
So whether EMI is finished or without EMI they went to AC.
They did not teach any other chapters. They directly taught chapters.
So without EMI they taught AC.
Yes, sir.
Sure? Kirti, easy, right? If you are hearing me, Kirti. Whether they not taught EMI and they directly went to AC? Okay, fine. Anyhow, because after EMI only AC should come. Without EMI, how can we learn understand AC? Because EMI consequence only is AC. Anyhow, no problem in that. We'll go step by step. But if you have any school exam from EMI AC, you let me know. I think by the time next exam will come, we will be reaching EMI AC all obviously. Okay. What about Velamal? What they are doing here? Completed volume 1 fully. 6th is going on. You are also from Velamal only. What about you? Okay, you are Sriniketan. So for you, they have finished volume 1 up to electromagnetic waves. From EMW, right? Very fast. Okay, what about Yash Praveen? Ask me Devadarshan. I think you are also from the same Nedugundaram school, right?
Yes, sir.
Tell me Devadarshan, tell me.
Why do they find magnetic field due to I1, sir? Why?
Why are they finding magnetic field due to the current I1 you are asking?
Yes, sir. First question.
Yes. What I am doing, see, pay attention. Because of one wire, I am finding how much magnetic field is produced here. Okay? And this magnetic field, we are keeping a conductor. So first I am finding magnetic field due to a current carrying conductor. Then I know that if you have a current carrying conductor and if you have a magnetic field, a force will act on it. So in this magnetic field, when I am having a current carrying conductor, second conductor I2, then how much force acts on it? That only we are finding. Are you getting a point, Devadarshan? Once again, in wire B, I have some current I2. By this current, what is the magnetic field here we are finding? And in this magnetic field, we are keeping a current carrying conductor which is having current I1. And we are trying to find what is the force acting on it. That comes in this direction. So these two forces are trying to attract each other. Okay, Devadarshan?
Yes, sir.
Okay, fine. Where are Sriniketan? What they do? Which chapter? Same chapter, no? Ask me, Krishna.
Sir, what happens if you include electric field, sir? Electric.
What happened if you include electric field also? You are talking about this case. What case we are given now?
The previous case, sir, force on current carrying conductor, when it is kept in magnetic field and as well as electric field.
See, if there is electric field will control the motion of the electrons or protons. Am I right? Either the charge will move more faster or slower. Right, Krishna? It totally depends upon direction of electric field. So based upon the electric field direction, there will be a force acting on the charged particle because F is equal to QE. And that will increase the velocity of the charge, right? If the velocity of the charge is changing, its current will change because I is equal to NEAVD. If the current is going to change, the force is going to change. So force may increase or decrease if electric field is acting here based upon how the electric field is acting. Are you getting my point, Krishna? Whether electric field is supporting the movement of charge or opposing the movement of charge. If it is supporting the movement of charge, velocity will increase. If velocity is increasing, force will increase, current will increase, force will increase. And vice versa. Got my point, Krishna?
Okay.
Yes. So I hope this is clear to you. But one more thing is there here. I talked only about a scenario when two wires were having current in same direction. There is a possibility one current is carrying current in the upward direction, second current is carrying current in the downward direction. Possible, no? Or vice versa. Then what will happen? It will, common sense it will repel, because if it is having like this, now once again we will use the same logic. Current in the upward direction towards right side, magnetic field is into the plane, magnetic field into the plane, current downwards, thumb acting towards right. So force in the this direction. Same way, current is down, magnetic field is into the plane, left hand rule, magnetic field into the plane, current upwards, force acting in this direction. So if two conductors are carrying current in same direction, they will attract each other. If they are carrying current in opposite direction, they will repel each other. Got my point? With what force? That remains same. Mu naught I1 I2 L by 2 pi d, where I1 I2 are the current carried by both the wires, L is length of the wire, D is distance between them. Is it clear to you? I hope it is clear to you. Now one more thing I will tell you. Do you know that if the question in the board exam you get a question, define 1 ampere, define 1 ampere, and if you write if 1 coulomb of charge is passing through a conductor in 1 second, then the current is 1 ampere. They will not give marks to you because you are not studying in 10th standard. In 10th you studied this I is equal to Q by T. If Q is 1 coulomb, T is 1 second, then I will be 1 ampere, right? 1 coulomb by 1 second, that is correct. But what they are expecting in higher class, how to define 1 ampere current, please pay attention. Now, we know that in this case or that case, whatever the case may be, F is equal to mu naught I1 I2 L by 2 pi D. Don't you agree with me? Everybody pay attention, something important I am telling for the examination. If I take I1 is equal to I2 is equal to 1 ampere, if I take length as 1 meter, if I take D as 1 meter, then see what is going to happen? F is going to become equal to mu naught. Mu naught is how much? 4 pi times 10 to the power minus 7. I1 is how much? 1. I2 is how much? 1. L is how much? 1. Divided by 2 pi. D is how much? 1. 2 pi will make it 2 times. How much will the force? 2 into 10 to the power minus 7 Newton. From here only we define 1 ampere of current. So, how 1 ampere is defined? Listen to me very carefully. I will speak and I will give notes for it. 1 ampere is that value of current which, when flowing through 2 wires of unit length having unit separation, observes an attractive force of 2 into 10 to the power minus 7 Newton. I will repeat this. 1 Newton is that current which, when allowed to flow through 2 wires of unit length having unit separation, producing a force of 2 into 10 to the power minus 7 Newton. If it is clear to you, write a definition of that. I'll say in words now. First you can copy this, then I will say in words the definition. First you write this, what I have written on the board, the equations. Shall I define it? Those who want to write, I will dictate for them. 1 ampere is that current, 1 ampere is that current, 1 ampere is that current which when passed through two parallel wires, through two parallel wires of unit length, having unit separation, experiences a force of 2 into 10 to the power minus 7 Newton. Experiences a force of 2 into 10 to the power minus 7 Newton. I hope you have written this. Okay, sometimes it comes in the examination. Remember, you will forget it, I know. So you will write same thing and come. Define 1 ampere. If 1 coulomb of charge is flowing through a conductor in 1 second, current is 1 ampere, they will not give marks to you. I am disclaiming this now. Okay, coming back. How the questions are coming from this topic in the board examination? Anyhow, ma'am will solve in the practice class also, but I will tell you now some examples. One very famous question comes, I have even seen in competitive examination. The question is like this. There will be a wire carrying some current, suppose 10 ampere current. Okay. Near to this wire, there will be a loop. This loop will carry some current. Let the current be like this, and let the current have a value of 5 ampere. Okay. And they will say this rectangle has a dimension of 3 meter cross 1 meter, having a separation of 2 meter from the wire. Now they will ask you, what is the net force on this loop and in which direction? Is my question clear to you? There is a current carrying wire having 10 ampere of current. In front of it, 2 meter away from it, I have a current carrying loop which is carrying 5 amperes of current. Dimension of loop is given to you. Separation of the loop and the current carrying conductor is given to you, and they may ask you what is the net force on the conductor. If you realize, please pay attention. If I am writing this as A, this as B, this as C, this as D, there are 4 parts in this loop. If you try to find the direction of the forces, you will realize that these two wires will be attracting each other. Am I right? F1. These two wires will be repelling each other. F2. It means I am having 2 forces on it. You may ask me about these 2 forces, I will talk about that also. I am having a force F1 trying to attract the wire towards 10 ampere wire, and a force F2 trying to repel the loop away from the wire. Which will be more, F1 or F2? F1. Why? Closer, because F is inversely proportional to D. What is the formula of F? Just now I told you. Mu naught I1 I2 L by 2 pi D. So D is less for this wire AB. It will have more force. The D is how much? 2 plus 1, 3. It is more, so it will have lesser force. So which is more? F1 is more. Net force will become equal to F1 minus F2. How much is F1? Mu naught. What is I1? 10. What is I2? 5. What is L?
2.
How 2? Yeah, this length. No, length is this, right? Common length. 3 by 2 pi. D is how much? 2. Minus mu naught I1 I2 L by 2 pi. D is how much? 3. When you solve this, you will get the answer. Are you getting my point? You may ask me, what about this BC and DA? Nothing they will do. They will also have force. But how the force will be? Let us try to find the force. So the current, is carrying in this direction. Okay. This will produce some force here, which will be acting in this direction. Some force in this direction. They will cancel out each other, isn't it? Whatever force acts here, same force is acting here. These two forces will cancel each other. There will be no force which will make it to go towards right or towards left. I hope you are getting my point. Because they have same value, mu naught I1 I2 L by 2 pi D. But these two will have a net force on it. Are you getting my point, what I am trying to say? So, this kind of questions are coming in the board examination. If you see the previous year questions, there are quite a good number of questions coming from here. Are you understanding my point? You see today, after going to home, I think all of you have got the book. All of you have taken the book. Varshita and Kirti, I think, Kirti, you have got the book, right? What about Anshul? You also got the book?
Yes, sir.
Okay, who has to get the book is Varshita and Kalaiselvan. You have not got the books, if I am right.
Sir, we are Shakti.
Oh, Shaktivel.
got it, sir.
Kalaiselvan also got the book. So, Shaktivel and Varshita, actually, you can get the book tomorrow. I think tomorrow somebody will be coming to your school, so they will be giving the books to you, okay? Yes.
Thank you, sir.
Anybody else? Saravanan, yes, have you got the book, man?
No, sir.
You will get after the board exam gets over? What, man? You want us to parcel the book to your home? You are staying in Gudvancheri, right?
Yes, sir.
Last 1 month you not got one day to come and collect the book here?
I will correct, sir. I will come.
Or shall I come tomorrow to your home and give the book to you? What do you want? Please, man, collect the book as soon as possible, okay? What about other people? Leah Varshini got the book?
Yes, sir.
Anybody who's sitting in the class, Krishna Raghav, okay, for you that book has been given, different book. What about other people? Mithun, have you got the book?
Yes, sir.
Pratap, have you got the book? If you are hearing me.
Yes, sir. I came and collected it. Yeah.
You collected, no? What about Deepa Jyoti?
Yes, sir.
Got the book and kept in the cold bed. You are using the book and solving questions from there or not?
Yes, I'm using it, sir.
Your intensity of yes is telling how much you are using the book. Saravanan I. The blurred Saravanan. Huh?
I got the book, sir.
You got the book. And what you did? Sold the book. What did you do with the book, man? Solving questions from the book or not? Have you solved even a single question from the book till now?
Sir,
Don't lie, man. Tell you honestly. Say no. What I will do? I cannot beat you also from here. What?
I found two sums, sir.
Very good. Good. Nitish Raghav, today only you got the book, right?
Yes, sir.
I think here, whoever is sitting, anybody is without a book?
It says ready to pair.
Who was that here? Huh? Ready to fare the, okay. I thought somebody from America joined. Okay, everybody here got the book? You have to get the book. Anybody else got the book? Not got the book? All of you got the book, right? I hope you are carrying the books in the practice class. Coming for practice class, no? If you are coming, please carry the practice class, that book. From there only we are practicing questions now. Okay. So those who have not got the book, please get the book soon, because with the books only you can learn here further. Okay. What we were doing? Okay. We were learning about. That will be fine. So see, in the last class we found what is the force on a moving charge kept in a magnetic field, and the force was QEB sin theta. Today we found what is the force on a current carrying conductor kept in the magnetic field. We got the values mu naught ILB sin theta. Then we found what is the force on two parallel current carrying conductors. We got the value as mu naught I1 I2 L by 2 pi d. And now we are going to learn next heading as torque on, not last topic, Thambi, almost here, torque on current carrying loop kept in a magnetic field. Torque on current carrying loop kept in a magnetic field. Leah Varshini slept, so off the camera. Saravanan, camera should not go off, Mr. Saravanan I. Okay. This application, shall I? This application, when it was found first time, it was a major breakthrough. Remember this. You may say that Orsted's finding was also a breakthrough, Biot-Savart law was also a breakthrough, and a lot of experiments did happen at the time, also a breakthrough. But this particular experiment or this particular discovery or this particular invention or this particular concept, whatever you call it, when it was applied in the real practical life, like how we say that wheels, when it came, it changed the whole world, right? It changed the whole world. Same way, when this concept was discovered, many new things came in the market. See, we were not knowing that by electric current, we can rotate something. And when we found it, we started making lot of things, the first being motor vehicles.
Motors.
Yes, all the motors, wherever motor is there, and you know, everywhere motor is there. Everywhere motor is there. You may see this as a screen, everything is very beautiful, but inside if you see, the motor will be there, running behind. Camera, looks, nothing is there, inside a small motor will be rotating. AC, a very huge motor is there. Fan, motor is there. Washing machine, motor is there. Grinder, motor is there. Mixie, motor is there. Grinder, mixie are almost same. I hope you are understanding how much, you know one thing, a refrigerator motor is there. Yes, man. Second law of thermodynamics, refrigeration, we want motor. So, motor is almost in all the electrical devices. Imagine life without motor, nothing will be there. So, that is why I said motor, when it was found, it was a great breakthrough in the history of physics. Not only this, even the vice versa of it, which is called as electromagnetic induction, that came by generator principle. That also is a very major breakthrough. I will talk about it in the upcoming classes. But remember that when I talk about motor, that motor works on which principle? This principle only. What principle? Torque on a current carrying coil kept in a magnetic field. Now, please pay attention without wasting any time. Please listen to what I say, you can copy it later. So, what I am doing, I am having two magnets. Why I am giving two magnets? Because I want to create a uniform magnetic field. North to south, there will be magnetic field lines. Am I right? If you want to create uniform electric field, what we do? We take plus sigma and minus sigma. We take two plates. One plate is having charge density of plus sigma. One plate is having charge density of minus sigma. And between those plates, we have a uniform electric field. Same way, if we want to have a uniform magnetic field, then what do? We keep one north, monopoles don't exist, I hope you know this. So, we keep one magnet there, one magnet here. Don't think how he wrote only north, this side south will be there, man, I have not drawn that. How I wrote only south, that side north will be there. But if you have a north pole, south pole, then in between them you have uniform magnetic field. In this magnetic field, what you are going to place? You are going to place a coil. When I say coil, what you can imagine is a frame of wire, like a wire. Are you able to feel what I am trying to say? A loop, like that you can imagine. And let me name this wire as A, B, C, D. So, I hope it is clear to you what I have done now. What I am doing is, imagine in this room, this side wall, my right, your left is north, my left and your right is south. So, I have a magnetic field coming from north to south, and I am going to place a current carrying coil, not just a coil, current carrying coil. It is not a coil, by the way, it is a lamina. Imagine it is frame, there is nothing in the center, imagine like that. So, I am keeping a current carrying coil in the magnetic field. Okay. Now, what starts happening? Just now you learned that if it is having a current, so current is going from D to A to B, B to C and C to D. Direction of current is clear to you? I hope it is clear to you. Okay. Let us see one by one each part of the wire. Please pay attention, it is something which you understand, or formula I can tell and go directly, but I want you to understand how the principle works, please. If you see DA part of the wire, magnetic field in this direction, right, in this direction magnetic field is there, current is in the upward direction for AD. So, the force will acting into the plane, but I have not drawn like this, I have tried to draw like this, some inclined way. So, now you imagine the magnetic field is in this direction, current in this direction, so there is a force acting in this direction, right, somewhere like this it is acting. Are you getting my point? So, I am drawing it something like this. Do you agree with me? It is into only, but I am drawing like this somewhere there, that side. If it is perfectly kept in this way, then yes, you can say it is into the plane. But I am not keeping in this way, I am keeping like this way, no, that is why I am keeping in that direction. Are you getting what I am trying to say? It is little difficult to draw on the board. It is in that direction. Are you getting my point or not? It is like this, so it is in this direction somewhere, the force. Okay. Now, what happens to the wire AB? Once again, magnetic field in this direction, current somewhere flowing from A to B, upward. Wherever it may be, it will always be upward only. Understand the difference between DA and AB. DA, as the coil is rotating, the forces keep on moving, right? But in the case of AB, whatever it rotates, it always acts in the upward direction only. So, force will act in the upward direction for AB. This was the force for DA. What will happen for BC? Current like this, sorry, magnetic field like this, current downwards. So, it is coming in outside direction somewhere, right? So, I am drawing like this, F on BC. And what is the CD doing? CD, magnetic field this direction, yeah, downwards, F on CD. As I said to you, if you have a coil in the magnetic field, wherever you keep the coil, this part which is actually AB in the diagram or CD will always have force in the upward direction. This will always have in the downward direction. Upward, downward cancel each other, no net force. But one force acting like this, one force acting like this will turn it. What will create? Couple. Couple is a condition where two forces equal and opposite are acting in different lines of action. It rotates something like dipole, isn't it? So, this particular coil starts to rotate. Why it starts to rotate? Because there is a magnetic field acting on it. So, then only we understood that, okay, if I have some magnetic field, if I keep some current carrying conductor, it will start to rotate. And why it rotates? Because this AD and BC part is creating a torque on it. And what is torque? Torque is force into perpendicular distance. First of all, what is force? What is force DA or force BC? Both have same value. BC, I should write BC. How much is that? Mu naught. Why mu naught you are saying here? I am not talking about the force because of two wires having opposite direction. And individually I am asking. Individually it is ILB sin theta, isn't it? So I will write I into length. Let the length be same L. See this. Let me assume it has a length L and it has a width B. Okay. So L and B. So I am write L, I, L. Magnetic field I am writing it as B into sin theta. Same will be for BC also, no? Current is I, length is same L because the rectangular frame, and sin theta. Are you getting my point? First draw this diagram. I will draw one diagram. First you draw this diagram. I will draw one more diagram to make it more clear for you, bigger diagram. First you copy this first. Middle plate. Huh? Obviously, it's not plate, it's a frame, wire, loop, coil. Don't call plate. Have you copied drawn diagram? Hmm. Hmm.
That force will cancel out this force, that FDA and FDC can, that two forces can be equal, sir, that FDA and FDC.
F
FDA and FDC, those two forces can be equal.
not can, it is equal, it should be equal only, because the force formula is ILB sin theta. So I is the current flowing through it, L is the length which is going to be same, B is magnetic field going to be same, theta is the angle made between L and B, right? It's going to be same for both because they are moving symmetrically. It's not like one is going like this one, it's going together, no man.
So I cannot cancel it.
They don't cancel each other. And they are, see, two forces can cancel each other only if they are acting in the opposite direction, right? Here, one is acting in this direction, one is acting in this direction. Even if they have equal values, they will not cancel each other, right? Because they have some separation. It will create torque. This is the object. If I pull from here and pull from here, they will cancel each other, same force. But if I pull like this and pull like this with same force, will it cancel? No, it will rotate it. Torque. Couple it is called as.
So in different axes, the opposite forces are acting also, you can cancel it.
If in different lines of action, it means that two forces, suppose it is acting like this, they will cancel. But one is acting like this, one is acting like this, they will not cancel. They will turn it. Are you getting my point? One is, if they would have acted like this and this, they will cancel, like this. But one is acting like this and one is acting like this, they cannot cancel each other. Are you getting my point or not? This will pull it, this will also pull it, it will make it to rotate. That only is happening. Okay? So, all of you I think have drawn and written. Please pay attention now. I'm once again going to redraw it. Only the upper part. Please pay attention. So, this coil, if I am drawing, I told, see this FDA I am drawing here for making it easy to understand, and FBC I am drawing here. It is like this, right? FDA and this is FBC, right? I told you torque is force into perpendicular distance, right? Force we found. What is the perpendicular distance from the force? What is this? Width B, isn't it? So, can I say that torque will be, what is the force acting? I, L, B, sin theta times, what is the distance? B. What is length into breadth? Area. So, can I say torque will become I, B, A sin theta. This is the torque on a current carrying coil kept in a magnetic field. If this coil has n turns, for n turns, F will become equal to N I B A sin theta. Remember this. So, N I B A sin theta is the force on a current carrying loop kept in a magnetic field. Very important, please pay attention. One more thing I will tell you, please wait 1 second. You will learn in the next chapter that N I, tell me man, something you are saying, Krishna, you are saying something? Devdarshan, please tell me. Torque?
Torque is equal to F plus A theta. Not F plus.
I am not able to hear you clearly, man. Can you see little once again slowly?
Sir, actually the torque only means NIBA sin theta. That you wrote F plus.
Yes. Okay, yeah, it is torque. Sorry, it's not F, it is torque.
That's what I done.
Okay, yeah, correct only. It is not force, it is torque. But torque will become equal to NIBA sin theta, and you will learn that NIA is called as magnetic moment. It will come in next chapter. I will teach you. Magnetic moment is equal to NIA. So, if I replace NIA with magnetic moment, I can write tau as MB sin theta. In vector form, I can write torque is equal to M vector cross B vector. So, remember this also. This will once again repeat in fifth chapter. It will once again come in the next chapter. But for now you can understand that NIA, number of turns into current into area of the loop, is also called as magnetic moment. Like how we have dipole moment, no? We have magnetic moment also. Electric moment was there, dipole moment, which was equal to Q into 2D. Same way here, magnetic moment is NIA. We will talk about that. Let the topic come. Okay. First you copy this fast. So N is number of turns, I is the current carried in the coil, B is magnetic field, A is the area of the loop, theta is the angle made between B and A, remember that. That is what is the direction of magnetic field, A is the area vector. Angle between magnetic field and area vector is only theta. So whenever loop is there, it will have some, like suppose loop is like this, then this is the area vector, isn't it? And this is the magnetic field. So this angle between these two is only called as theta. Are you getting my point? If magnetic field is in this direction and this is the direction of loop, this will become the area vector. This and this, what is the angle between them? That is only called as theta. If you have copied, let me know. We will start the next topic, which is very important, MCG. Shall I continue? All of you are done? So we have understood that if you have a moving charge in magnetic field, force is QEB sin theta. If you have a current carrying conductor in magnetic field, it is F is equal to ILB sin theta. And if you have a current carrying loop kept in magnetic field, it is torque, which is NIBA sin theta. Is it clear to you? All these three are similar, but they are having their own applications when it comes to the numericals and questions. Okay. Can I go to the next topic now? Shall I? Okay. So give the next heading as moving coil galvanometer. Moving coil galvanometer. So with this, let me ask question to Mr. Hemant. What do you mean by a galvanometer, Hemant? What is a galvanometer? Yes. Have you heard about galvanometer before? Definitely yes, you should have heard. What is the use of a galvanometer? Where we are using it? This much time you should not take. Harvish, what is a galvanometer?
Sir, to measure the current, sir.
To measure the current, then for what we are using ammeter, man, Harvish? To measure potential difference. You told galvanometer for measuring current, right, Harvish?
Yes, sir.
Then for what we are using ammeter? Think and say.
Current, sir.
Then why we are using galvanometer, ammeter for both the same things?
Sir, it is to measure the deflection produced by current in magnetic for magnetic field, sir.
So you are
If
thinking.
we keep chalky, it will show deflection.
Okay, wait, control. So you are thinking that galvanometer can be used only if magnetic field is there. We have so many galvanometers in market. Direction of current. Okay, good. Some other points from you? Akhilesh, anything? Sai Akhilesh, any idea? Galvanometer and ammeter, how are they different from each other?
Predicting the direction of current.
Oh, you also okay. Okay, so you have also seen the galvanometer which is starting like this from the center, this side plus, this side minus. Am I right, Mr. Akhilesh?
Yes, Yes, sir.
If it goes right, the current is going like this. If it goes left, current is going like this. You are not wrong, but that is not the only reason why we are using galvanometer. Kirti, any idea about galvanometer? How is it different from ammeter? Okay. Anybody else voluntary? If you want to say something about galvanometer, you can say. Please, Shakti, Sharan Ram. Yeah, one second. One second. Let him say, then you can say. Yes, Pratap.
The galvanometer is used to measure like minute differences, whereas ammeter is used to determine the magnitude of the current flowing through the circuit.
I'll come back to you. Good point. Yes, what you are saying, Sharan Ram.
Sir, even if a small amount of current is present also we can find it galvanometer.
But in ammeter, no, we will not. We cannot. Why? Big value means how much big value? 10 ampere, 20 ampere. Then how much? 1 ampere. Something when what? Big value is what? Good, good. You people are right. Pratap, you both also, all of you, all three of you are correct. See, guys. First of all, Mithun, Devadarshan, Sai Akhilesh, whoever told some answers, you are not wrong. But when galvanometer comes to your mind, you are thinking only about the galvanometer which is working towards left or right direction. This galvanometer will not measure current at all. It will be used just to see whether the current is coming towards right or towards left. But we have some galvanometers which can also measure current. And you know one thing? It can measure a very small amount of current which sometimes cannot be measured by ammeter. What ammeter you would have seen in school, it may be like 0, 1, 2, 3, 4, 5 or 0, 10, 20, 30, 40, 50 like that. So, suppose it is having a reading of 0, 10, 20, 30, 40, 50, then between 0 and 10 there are 10 divisions. So, we are going to measure 1 ampere as the minimum current. If the current is 0.1 ampere, it will not measure itself. Okay, I am having some good ammeter, I am having 0, 1, 2, 3, 4, 5. Then between 0 to 1 we have 10 divisions. I can measure 0.1 ampere. But what if 0.01 ampere goes in the wire? It won't measure, because the minimum deviation, it is called as least count. The least count of your galvanometer or the ammeter is 0.1 ampere. If the current is 0.01, 0.001, 0.000001, cannot. But even a microampere current can be detected by whom? By a galvanometer. So, galvanometer is not only used to find the magnitude, direction of current, it is also used to find presence of very feeble current, very feeble current, because it works on the principle of torque on a current carrying coil kept in a magnetic field. So, you please write the principle first. Principle of MCG is, write the principle. It works on the principle of torque on a current carrying coil kept in magnetic field. It works on the principle of torque on a current carrying coil kept in magnetic field. It works on the principle of torque on current carrying coil kept in magnetic field. Torque on current carrying coil kept in magnetic field. Okay, now please pay attention. I will give time for writing. We don't have much time left now. So, I will just give you some idea about this topic. Please. So, how the logic is, very simple logic is there of MCG. We know that whenever a current carrying coil is kept in magnetic field, it will have a torque on it. So, imagine I am making galvanometer. In the galvanometer, I am having two magnets, permanent magnets, to create magnetic field. In that magnetic field, I keep a coil, and that coil I am having two terminals, one towards positive, one towards negative, like that I made two terminals. And my circuit, if I am attaching in the MCG, in my plus and minus, even if small amount of current is coming in the wire, the magnetic field of the magnet and the current in the coil will create a torque inside, and torque will make the coil to move like this. If the coil moves like this, the arrow also turns like that. If arrow is turning, it is very clearly visible that some current came inside. Logic is very simple. What logic is there? We have a coil inside, we have magnets inside, so we have a magnetic field. Since I have a coil, and if I attach that my MCG with the circuit, if a small current also is coming inside, it becomes like current carrying coil kept in magnetic field, and this current carrying coil kept in magnetic field will give a torque on my coil will rotate, and my coil rotates. In my coil, what will attach? My needle will be attached. Needle will deflect, showing some current has come inside. But there are a lot of problems. The first problem is the torque. The torque depends on, saw the dream? Chewing gum or what you are eating? So what you are chewing your tongue? Then lot came from Maharashtra yet? Came, no? Memories. Why? Be in the class. Don't disappear somewhere, please. Coming back. So I was talking about problems in that MCG, that is problems in making galvanometer. We understood that if current will come, torque will deflect my needle, needle gets deflected, definitely you are going to see some current has come. Problem is, torque formula is NIBA sin theta. What is theta there? Angle between area vector and magnetic field. Imagine angle between area vector and magnetic field became 0 degree or 180 degree. What is sin 0? What is sin 180? It means that even after the current is coming inside, since theta is 0 or theta is 180, your deflection will not be there because torque will not act. Are you getting my point? I is there, B is there, A is there, but theta became 0. First problem. Second problem, theta was having some good value, 90 degree assume, and we got some good deflection. My needle went like this. I have to use my galvanometer second time also, no? Needle has to come back, right? Or else from here, where it will go? It will break it will come out. Huh? It has to once again come back, no, or not. Then only I can use it second time. Or for every experiment you will use new galvanometer. No? Or you will break the glass of galvanometer and by hand you will make it like this. Impractical, right? So the second problem is, how will my needle come back to its original position after the current is not there? Current is there, it can show. Current off, it should come back, no? Current is there, it is deflecting. I am offing the current. It will not come back itself. It is not human being, it will come back. It has to do something by us to make it to come back. He said spring. I will come to that point. So the two problems you understood. The first problem is dependence of torque on theta. Second problem is making my needle to come back to the original position after the deforming torque is removed. Not deforming, the deflecting torque is removed. So I will talk about both these problems, how they solved. So first problem was theta problem, that was solved by using a radial magnetic field. If you see your NCERT book, you will have a very good diagram there where they have drawn the magnets like something like this. Not very good in drawing, but something like this. These two parts, it's not like simply drawn. It is making sure that theta always remains how much? Wherever it rotates, however it rotates, the angle made between magnetic field and area vector will be always 90 degree. That will make my deflecting torque to have only one formula, NIBA, because theta is 90. Dependence theta got over. Now no tension, because by using radial magnetic field, I made sure that my theta always remains 90 degree. Second problem was, when my needle got deflected, it has to come back. For that reason, as you told, yes, we are using spring. So we are using spring and we are putting spring down. What will happen? The moment it is deflecting, spring also rotates. You know about spring, it has restoring force. The moment the current is not there, it will once again bring back to the original position. Spring should be good enough. If it is some bad quality spring, it will not come to the 0 point. Then you will have some error in your galvanometer. In your school, sometimes it is not in 0, no, it is somewhere between 0 and 1. Error is there, means spring has failed. Are you getting my point? If spring is of good quality, it will make it to go back to once again 0. So that will be a restoring torque. And restoring torque is purely given by whom? Spring. So I should make a spring in such a way that the restoring torque is depending upon angle of twist. I am taking theta as what? Angle of twist. Angle of twist means how much angle it rotates. Do you agree with me or not? Because if it is more twist, I should have more torque. If it is less twist, I should have less torque. It should not happen like less twist came, more torque came, it goes and breaks that galvanometer. Or if less torque is coming, it goes to the full deflection, it will not come to the original position. So I want exactly my restoring torque to depend upon how much deflection I am giving by theta. So if you do this, you will get that tau restoring is equal to proportionality. If it is removed, we have to add a constant. Let me write it as k. Tau restoring will become equal to k theta, where k is a constant called as what constant? Torsion constant. You remember this similar thing has come in 11th standard work energy and power, also in oscillations chapter. F is equal to kx. K is equal to F by x. Here k is equal to tau by theta. F was what? Force. Analogy, torque. X was displacement. Analogy, angular displacement. Right? So for equilibrium, torque deflection must be equal to torque restoring, isn't it? So for equilibrium, what I will write? Tau deflection equal to tau restoring. So what I am going to get? NIBA equals to what? K theta. Now you see here, you will realize that theta became equal to NIBA by K. This I can write from here. N is number of turns, going to be constant. B is magnetic field, going to be constant, because magnetic field is provided by whom? Permanent magnets. It will not be varying, it will be same. A is the area of loop, going to be constant. K is obviously a constant. It means my theta started depending upon what? Current. That only I wanted, no. I want how much current is coming, that much deflection should happen. Less current, less deflection. More current, more deflection. Then only I can measure the current. How you can measure the current? If the current coming less, my deflection should be less. If more current is coming, more deflection. So I want my deflection should be proportional to current, and I got it by this. So first you copy this. One small thing is there. First you copy this fast. I don't have board. Have you copied? Make it fast, please. Time is already going to be 9. One small thing I will tell you before I leave you. Shall I? I hope you have copied this. Shall I tell some more things to you? Some very basic things to you. So from here, if I want to write what is I, what will be I? I will become equal to K by N, tau where it's there, man, NBA into theta, isn't it? Right? This K by NBA is called as what, you know? Capital G. It is called as galvanometer constant. So they ask you what is galvanometer constant? It is K by NBA. And what is that? I by theta. Whatever you want to, you can write. It has another name also. What is that? Anybody knows? Velamal taught this chapter. This is also called as figure of merit. It comes in the board exam sometimes. Figure of merit, or also called as galvanometer constant. Whatever you want, you can write. Remember both. So if they ask you what is figure of merit, what you should write? Current per unit angle of twist is called as figure of merit. Or if they ask you what is galvanometer constant, current per unit angle of twist. Are you getting a point? So I by theta is also called as galvanometer constant or galvanometer, figure of merit. It comes in the exam also. So in this chapter, one small topic is remaining, sensitivity of galvanometer and how to convert galvanometer into voltmeter or ammeter. Important topic and simple topic also. If I had 20-25 minutes more, I should have done that also now. But I will do it in the next. Start magnetism also in the next class. Next class, I will be not only finishing this chapter, I will be starting also the magnetism and matter, the 5th chapter, small chapter. Okay. So with this, let me end my class now, and we will meet once again in the next class. Okay. Girls can move and then boys will move next. Guys, those who are copying the notes can copy the notes. Those who have done, they can start leaving the meeting. Take care. Bye bye. Good night.